Okay, so now let's take a look at 9.5 kinetic molecular theory. There is literally one page on this. I don't want to get lost in the minutia. I'm going to throw a handful of equations at you, and we're going to talk a little bit about kinetic energy and velocity and stuff like that. But ultimately, the most important thing here is just to recognize that it makes the fusion, the size of molecules is going to determine the speed. So kinetic molecular theory has 5 postulates or 5 rules. By the way, you also see it in your book, and I encourage you to read your book if you want to kind of get the derivations down, because I'm going to kind of skip the derivations of all this stuff. So KMT, kinetic molecular theory. Gases consist of large numbers of molecules that are in continuous random motion. Okay, so we have a container, we have a bunch of molecules, and we know that they are continuously random motion, going anywhere that they want to go. We'll talk about the energy and all of that in a little bit, but temperature ultimately is kind of the average energy of all of the molecules combined. It's just kind of, it is equated to speed, but well, we'll see the relationship. 2, the combined volume of all molecules in the gas is negligible relative to the total volume contained. So it's important to say that the amount of gases are moving incredibly fast. They are very few and far between. So the number of gas particles can be compressed to a infinitesimally small space as compared to the space that they're in. So the classroom that I'm sitting in, the room that you're sitting in right now, if you took all of the gases in the room and shrunk it down, it would be minuscule and compared to the space. Okay. All right. Attractive and repulsive forces between gas molecules are negligible. So what this means is this allows them to transfer energy. They're not going to interact with one another. And we'll talk about why they start to interact with one another when we look at real gases, but they're not going to interact with one another ultimately all that much. So they just bounce off one another. They have no interaction whatsoever. What this also says is that gas molecules behave just like other gas molecules. Gas A equals gas B in terms of behavior. Okay, so they behave the same. They might weigh slightly different in slightly different amounts, but they behave the same. So we can kind of ignore the type of gas in most cases. 4, energy can be transferred between molecules during collisions, but as long as temperature remains constant, the average kinetic energy of the molecule doesn't change. So here we have the average kinetic energy of the molecule does not change with time. As long as temperature remains constant, we are equating temperature and kinetic energy together. So let's take a look at kinetic energy, and we'll actually take a look at kinetic energy a little bit. And let's see, I do want to mention, so I'm going to just kind of bounce around here in terms of the numbers, but kinetic energy, the average kinetic energy of a group of molecules, or the average kinetic energy of a system, is 3 halves times RT. So again, temperature is related to kinetic energy because those are the only 2 variables, right? Temperature and kinetic energy can change. R is a constant, and so is 3 halves. Okay. Good. So the average kinetic energy of molecules is proportional to the absolute temperature. So we've already seen the average kinetic energy, and I guess I probably should have just put this below. The average kinetic energy is equal to 3 halves RT. So we see that there is a relationship between energy and temperature. Now, the kinetic energy, let's briefly talk about the kinetic energy of kind of a mass of a particle. Is kinetic energy is equal to 1/2 mass velocity squared. So again, mass times velocity squared. This is the important equation that we're actually, or the important graph that we're going to take a look at. And we kind of already saw this, but we're only looking at 2. So I have oxygen at 2 different temperatures. So temperature changes. What we see is oxygen is going to change as well. So we have 2 different humps going on here. So first of all, the average kinetic energy is greater in the higher temperature oxygen, as we can see, because it's moving much quicker. And we know that the average kinetic energy, because it's at a higher temperature, it has a higher kinetic energy. So there's two values that we're actually interested in looking at this graph. Is this the one I want to look at? Sure. Yeah, looking at this graph, we've got two things that we're interested in. So first of all, we have two speeds that we're interested in. The peak up here at the very top. That peak up there is the velocity P. That is the most probable velocity of the molecules, the oxygen molecules. If you had to check a molecule, wait, how fast are you traveling? How fast are you traveling? Most probably it's going to be, just above 400 meters per second. But because this side of it is more spread out than the other side, the other value that we're interested in, and really the one that we're most interested in terms of this conversation, is about here. This is the root mean square, RMS speed, the root mean square velocity. The root mean square velocity is kind of the actual speed these things are traveling at on average. Okay, so most probable is not the same as average in this case because that one leg is kind of extended quite a bit. And we can actually determine the root mean square speed by looking at it is a square root. Again, you can go through the derivation if you want to, 3RT all over molar mass. Why is this important? Molar mass and root mean square speed, as we saw in the previous one, are related to one another. And we can, again, look at this. The higher the lower the molar mass, the higher the root mean square velocity. Okay, so the faster it goes. And that's actually what I said on the previous one. So a couple of things: root mean square speed for oxygen, root mean square speed for oxygen at a lower temperature. Hotter is moving much quicker, has more kinetic energy. All of that makes sense. Again, going back to the previous section, talking about in terms of molar mass, the larger it is, the slower it is going. Now, this is important. The slower that it is going, but again, the kinetic energy is going to be equal. Because it's moving slower doesn't mean it has less kinetic energy, because remember, kinetic energy is equal to 1/2 mass times velocity squared. That mass term is going to be important. The heavier it is, the more kinetic energy it can have. So krypton can be moving slowly, quite a bit slower than helium or hydrogen, but because it has mass, it actually has quite a bit of energy as well. So that is the kinetic molecular theory in a nutshell. I encourage you to kind of take a look. I think I got all the major equations. It's not really too much that we're concerned about, but yeah, so that is the root mean square speed conversation, talking about energy. Again, the higher the temperature, so just to sum up, higher the temperature equals a higher kinetic energy on average. Okay. The higher the molar mass, the higher the root mean square speed. And actually, the higher the temperature, we have a higher root mean square speed as well. Okay. And that is that. Again, temperature is a measure of, is about equal to the kinetic energy average, or I should say, those two are related through that equation above. Okay, so there is a relationship between those two, but I'm not going to write that down as gospel. Okay, good. All right, so we're going to take a look at non-ideal behaviors next, where we have some intermolecular forces and other such stuff. You don't really run into this that often, but yeah, that's it.